Welcome back everyone. I cannot believe we are back here already, but in this video I will be discussing dot point, it's point 7, or the use of Ricebox to calculate concentrations and other quantities relating to equilibrium constant, or Kc. This is just a method to do certain types of questions relating to equilibrium, so you don't necessarily have to use this method to solve the question, but it is quite useful, and I think it minimizes the chance of making an error. So I'm just going to introduce the method. We're going to start with example 1. So you have 4 mole of hydrogen iodide. So let's just be a good student and start by summarizing the question. So I have 4 mole. So the number of mole of Hi is 4. And 4 mole of hydrogen iodide was admitted to an evacuated. Now this just means that you have no other gas present in the reaction vessel. So no other gas present. And the volume of the vessel is 2 liters. So V is 2 liter. So you put 4 mole of hydrogen iodide in a 2-liter vessel, and you allowed it to reach equilibrium at a constant temperature according to this equation. So according to this equation, it looks like hydrogen iodide can spontaneously decompose into hydrogen gas and iodine gas, and this is a reversible process. So naturally, if you start with hydrogen iodide, or Hi, the system is going to go forward to use some of that hydrogen iodide to produce some hydrogen and iodine gas. And then they tell you that at equilibrium, 0.25 mole of iodine had formed. So there is a clear distinction here in terms of the quantities that are given to you. The number of mole of hydrogen iodide that is given, this is the initial amount. So this is not the amount of hydrogen iodide at equilibrium. So I tend to put like an I just to distinguish, because you can have multiple amounts for the same substance at different points, like at the start when it is at equilibrium, when you add some extra. So you really want to make sure when you summarize the question that you distinguish between the initial amount of something and then the equilibrium amount. So the last piece of information I'm given here is the equilibrium amount of iodine, which is 0.25 mole. Okay, so you have initial amount of the reactant and you have the equilibrium amount of one of the products. The question asks you to determine the equilibrium constant, so I'm after Kc for this reaction. Now I guess the starting point here is to start with the unknown, which is Kc. So in order to calculate Kc, I'm just going to write the expression here. You need concentration of hydrogen in mole per liter multiply with concentration of iodine in mole per liter over concentration of hydrogen iodide square. So I need to work out, and all of these are supposed to be equilibrium concentrations. So I need the concentrations at equilibriums of all 3 species. At the moment, all I have, so equilibrium concentration for all 3. At the moment, all I have is the number of mole of iodine at equilibrium. So I can use this triangle. If you really like triangle, you can use this triangle to work out the equilibrium concentration of iodine from the equilibrium number of mole of iodine. But I don't have any information regarding the concentration or amount of hydrogen or hydrogen iodide at equilibrium. So before you can work those things out, you cannot answer this question and calculate Kc. One thing, and we're going to talk about the Ricebox in a second, but whenever you see a question that gives some information on the initial amount, so we have one piece of information that is the initial amount, and then you have some information on the equilibrium amount. Whenever you see that, that is an indication that you can use the Ricebox method. You don't have to, but you can. I think with this question, you should be able to solve it even without using the Ricebox, but most people find it quite useful. So what is the Ricebox method? Essentially, the Ricebox sometimes is called rice table or ice table, which is the old name. It is a way to summarize and track changes to reactants and products in a reversible system as it reaches equilibrium. So essentially it is a table or box, and rice stands for reaction, initial amount, change, and equilibrium amount. So 4 letters. So let's just go back to this question. I'm just gonna see how we can fill the rice box with the information given in the question. So the first thing is the reaction. So the reaction is 2Hi going to hydrogen and iodine. So you can just copy the reaction as it is into the reaction row. Make sure that you include the coefficients. You know that the initial amount of hydrogen iodide is 4 mole. So I'm just going to put it in here right underneath the hydrogen iodide column. So some people do put like columns here, but I tend not to. I just can't be bothered. Well, we can put it in. That's okay. And then you also given the equilibrium amount of iodine, which is 0.25 mole. So the one thing to make sure that you do is the unit that you use in the rice box has to be consistent. So if you start with 4 mole, so if you use number of mole for the initial amount, you have to use number of mole for the equilibrium amount. You could convert both of these to concentrations, that's okay, but they just have to be consistent. Like they have to be the same. Now, one other piece of information that is actually given in the question, not explicitly, is the initial amount of hydrogen and iodine gases have to be 0, because the question say that you start with only hydrogen iodide. So that's the other two numbers that you can add to your rice box. You have 0 of hydrogen at the start and you have 0 of iodine at the start. So that's the rice box. That's all the information from the question summarized in the rice box. The main thing, and that's just the same thing again, the main thing that you can do once you have this is you can start filling in the rest of the box or table. And this is the first one. If you start with 0 mole of iodine and you end with 0.25 mole of iodine, it means that you must have added or plus 0.25 from the original amount. And this is from the forward reaction. The thing is, if I have produced 0.25 mole of iodine, I have to also produce 0.25 mole of hydrogen. And the reason for this is because the mole ratio between hydrogen and iodine is 1:1. So you have to obey mole ratio in the change row. This is mole ratio between hydrogen and iodine. So if iodine goes up by 0.25, hydrogen has to also go up by 0.25 because of a 1:1 mole ratio in the reaction. And if each of these substances has gone up by 0.25 mole, it means that hydrogen iodide must have gone down by twice the amount because of the mole ratio. And also, if the products go up, the reactants have to go down. So the sign has to be the opposite of each other for it to make sense. You cannot have everything going up. Like, where does extra stuff come from? So this has to be 2, again, because of the mole ratio. So if you look at the equation, the mole ratio between iodine and hydrogen iodide is, well, just a 1:2. So you should have twice the amount of hydrogen iodide. So mole ratio, if we go n of Hi is equal to 2 times, let's just move this on this side, n of I2. Okay, so once I can write one row, the beauty of the change row is if I have one number in the row, I could use mole ratio and fill the rest of the table. And I think it makes sense because in order to produce 0.25 mole of iodine, you must use up 0.5 or twice the amount of hydrogen iodide, and you should produce 0.25 mole of the product as well. And then once you have that, you can, I think I should maybe just delete that slide. Once you have that, you can just calculate the answer. So you would have whatever that is. You get 3.5 mole of product here. This is the equilibrium amount, and you have 0.25 mole of the product here. This is a reactant. This is also the equilibrium amount. Now, this is not the end. I need to then calculate the equilibrium concentration from the equilibrium number of mole. And remember, originally we had the volume of the reaction vessel to be 2 liter. So you have to divide the number of mole by the volume in order to get the equilibrium concentration. So this is 0.25 divided by 2. And this is also 0.25 divided by 2. Okay, so once I had the equilibrium concentration, I could find the equilibrium constant, which is the unknown in the question. So this is the final answer. So the key thing here is probably the change row. You have to make sure that you obey mole ratio, and there is actually a difference in the size. So if the products go up, the reactants have to go down, and vice versa. So that's it. That is it for the rice box. That is example